Hello everyone, thank you so much for joining this talk. My name is Jairo Giraldo and today I'm going to present an introduction of our work that is entitled DARIA, which is designing actuators to resist arbitrary attacks against cyber-physical systems. This is a joint effort between the University of Texas at Dallas, the University of California in Santa Cruz, and the University of Utah. The focus of our work is in cyber-physical systems, which consist of a physical process that is controlled using computers, communication networks, and embedded devices, and it spans a wide variety of applications. For example, water treatment plants, autonomous vehicles, electricity power grid. Unfortunately, attacks in CPS are becoming more common. For example, in Ukraine, there was a huge outage caused by a cyber attack. Similarly, there has been some malware that has been affecting the safety systems designed to prevent catastrophic industrial accidents. As a consequence, there is a huge need to design defense mechanisms that prevent these cyber-physical systems to be affected by cyber attacks. Typically, defenses for cyber-physical systems are designed considering very specific types of attacks. For example, there are defenses against replay attacks, others against denial of server attacks, others against false data injection attacks. And as a consequence, all of them offer limited proofs of security. Besides, they are like typically cyber defenses to counter cyber attacks. And in our work, we propose a design mechanism that allows us to protect cyber-physical systems against any type of attack, against arbitrary attacks. In other words, we don't make any assumption about the type of attack that is affecting the system. As a consequence, we are able to prove and guarantee security against this type of attacks, and what we offer is a physical defense to counter cyber attacks. In order to understand the intuition behind our main idea, let's consider this very simple example. In this case, we have a PLC that takes the water level sensor readings and computes the valve opening to keep a desired level of water. So for example, in this case, we have 1 liter of water per second coming in, and we have 1 liter of water per second coming out. As a consequence, the level of water is going to remain steady. However, when an attacker opens the valve at 100%, the water inflow is higher than the outflow, so the tank can potentially overflow. However, our defense strategy consists on adding some secure constraints that are going to limit the maximum valve opening percentage. As a consequence, the maximum inflow of water is going to be 1 liter per second, independently of the type of command that the PLC is sending. Therefore, if an attacker affects sensor readings or affects the PLC control commands, the system is going to remain safe. In order to translate our idea to a mathematical model, we first have to define what is called the reachable set, which consists of the set of states, like temperature, velocity, level of water, that can be reached by any attack sequence. Unfortunately, computing this exact reachable set is intractable, but it is possible to find an ellipsoid, like the smallest ellipsoid, that contains that reachable set. As we know, cyber-physical systems have very well-defined unsafe states. So for example, if the water overflow that we saw previously, then we can say that if the reachable set intersects with the unsafe states, then the system is unsafe. Then our idea is to find the largest group of constraints that can shrink that reachable set in order to guarantee the security against any attack sequence in sensors or in control commands. In order to find those secure constraints, we're going to use some tools from control theory and system modeling that are called state space representation. So in this case, we can represent the dynamic behavior of a physical process using this simple linear equation. So for example, X represents the system states, which are the pressure, velocity, temperature. U represent the control commands, for example, valve opening, acceleration. And each of these control commands are bounded by some very specific physical constraints. For example, maximum voltage or current that is available for a specific actuator. And A and B are matrices that are helpful to describe the dynamic interaction between the states and the control commands. On the other hand, unsafe states can be mathematically defined by the union of hyperplanes that are described by this equation. Just for simplicity, in this particular example, we have the reachable set, which are represent like pressure x2 and temperature x1. And in this case, the unsafe states are represented by this equation, which consists on all the points that are behind this line. And in this case, this other hyperplane represents all the points that are below this line. Having the mathematical formulation allows us to find that new group of constraints that guarantee that the reachable set does not overlap with the unsafe regions. To do so, we just need to solve this optimization problem. I'm not going to go into the details about this problem, but there are very interesting things that we can see here. The first thing is that we only need to have the knowledge about matrix A, matrix B, and the terms C and V from the hyperplane that define the unsafe states. So only having that knowledge and solving this convex optimization problem results in those optimal constraints that guarantee the security of the system. In order to illustrate our approach, let's consider the platooning example, which consists of a series of vehicles that intend to keep a constant distance between them. In this case, we assume that we have 4 vehicles, and each one of them has some sensor and control capabilities in order to maintain that distance. However, an adversary can compromise some of these vehicles, and the intention is to start accelerating and decelerating in order to make some of these vehicles to crash. In this case, we are going to consider several examples. The first example is when one of the vehicles starts accelerating and the other one starts decelerating. After 2 seconds, the vehicles crash, which is represented by the distance being 0. Now, if we reduce the constraints of the actuator constraint, the maximum acceleration and deceleration, we can see that the same attack strategy does no longer is effective and cannot cause any crash. However, an adversary that knows the system can still find a very specific trajectory that can cause the vehicles to crash. In this case, we can see that if the adversary causes some sort of oscillation, like acceleration and deceleration, then after 8 seconds and after some oscillation, the vehicles are going to crash. However, if we apply our approach, we can find the optimal set of constraints that guarantee that there does not exist any sequence that can drive the system to crash. The figure shows the reachable set for the different cases that we illustrated before. Here we can see that when we start reducing the actuator constraints, that overlap between the reachable set and the dangerous state start becoming smaller. And with our proposed strategy, we are able to guarantee that the reachable set does not overlap with the dangerous states. As another example, we also tested the quadruple tank system, which consists of these 4 tanks, where an adversary has the intention to overflow some of these tanks. However, when we apply our strategy, we are able to see that none of these different type of attacks, bias attacks, random attack, sensor scaling attack, is able to actually cause any overflow. In conclusion, we are the first ones to propose and formally study the modifications of the dynamic range of the actuators as a security defense. As a consequence, what we obtain is an offline design, proactive defense, and provable security. The limitations is that the control system might not be as responsive as before, and for this reason, it might not be applicable to all control systems. In future work, we want to study that optimal trade-off between performance and security. Thank you so much, and please feel free to contact us if you have any questions or any comments about this work. Thank you.